guys, this is Jadav. I'm a third year student from IIT Kharagpur. Now I'll teach you the two most interesting topics of gravitation. The first one is orbital velocity and the second one is escape velocity. Let's get started with orbital velocity. Now I'll write the definition first. So the definition is the minimum velocity required for an object or body to revolve around another object in a fixed orbit. I'll explain with the diagram. Let's say we have an object of mass m1 here which is fixed, and let's say we have an orbit. So this is typically a circle, and as center as the m1, the radius is r, and let's say we have another object mass m2 and which is revolving in this fixed orbit around this mass m1. Okay. So the minimum velocity we have to provide to this m2 so that it should move in this fixed orbit around this m1, and it should not go radially outward or inward. So this is the, now we will derive the formula for orbital velocity. Let's say we have a mass m1 here which is fixed at the center of the circle of radius a, and we have another object m2 which is revolving in this orbit of radius a with some tangential velocity, let's say v0, and which is the orbital velocity. Now as this m2 is just revolving around in this fixed orbit, so this is not either moving outward nor it's moving inward. So from this we can understand that the net force acting on this m2 in the radial direction is 0. So if you take at any point, this m2 is just revolving in this fixed orbit, but it's neither moving outward nor it's moving inward. So from this we can understand that in the radial direction, the net force on this m2 must be 0, right? So if I am taking the m2 here, let's say this body is not moving here in this direction, nor in this direction. So what can we say? The net force acting in this direction is 0, right? So if we are taking this m2, due to the velocity v0, it has an outward force which is the centrifugal force, and due to the gravitational pull between this m1 and m2, this m2 has an inward force. I mean, an inward force is acting on this m2, which is the gravitational force due to this m1. So this outward velocity is centrifugal force, and this inward force is centripetal force. Right? And this centrifugal force is due to this velocity v0, and this centripetal force is due to the gravitational pull between this mass m1 and m2. Right? So if I am looking from the reference of m1, then this object m1 is pulling this m2 inward. So now I am balancing the forces. So the centrifugal force, this one, let's say this centripetal force is gravitational force, so I am writing as Fg, and this centrifugal force, let's say FCF. This is the gravitational force, that is nothing but this gravitational force is nothing but G, gravitational constant, into mass m1 and mass m2 by the distance from the center of these two masses is A. So A square. This must be equal to the centrifugal force, and which is arised because of this velocity V naught, a tangential velocity V naught, and that is mv naught square by A. So A is the radius of this circle, radius of this orbit. Now cancelling A and A square, and this is the m2. This is the mass of the object which is rotating in the circle. So m2 and m2 get cancelled. So gm1 by A is equal to V naught square. So this V naught is simply root over G into m1 by A. So this is the formula of orbital velocity. So which is root over G into m1 by A. G is the gravitational constant, m1 is the mass of the body which is fixed at the center, and A is the radius of the orbit. So this is nothing but the distance between the center of mass m1 and the center of mass m2. So the two important note that you need to remember is, if you look into the formula V naught, then V naught is equal to root over G into m1 by A. So you cannot see m2 here. So we can say that the V naught is independent of m2. So the orbital velocity is independent of the mass of the object which is rotating. This is the one point, and the another point is this V naught is dependent on A, which is the radius of the circle, which is the radius of the orbit. So this V naught is inversely proportional to the distance, or inversely proportional to the radius of the orbit. This V naught is inversely proportional to the radius of the orbit. Now let's discuss the escape velocity. Now I'll write down the definition first. So the definition says the minimum velocity that a body should possess in order to escape from the gravitational attraction of a planet or any object. Okay. So let's say we have a planet here, maybe Earth, and when we send satellites into the space, or when we send satellites to the Mars, let's say, so this body should escape from the gravitational attraction of the Earth in order to reach the Mars. Okay. So this body should be subjected to a certain velocity so that it has to escape from the attraction of the gravitational force or gravitational attraction of this Earth or this any planet, so that it can go to the other planet or into the space. So that is the escape velocity. Now we will derive the formula for escape velocity, and the important concept to derive this formula is the conservation of energy. So we need to conserve the energy at two different points to get the formula for escape velocity. So before that, I'll tell you what is the gravitational potential energy. Let's say I have a mass m1 here, and I have another mass m2 here, and the distance between center of these m1 and m2. So I'm saying like the distance between the center of mass m1 and m2. So that is, the distance is not from the surface to surface, but instead it is the distance from center of this m1 to center of this m2. Let's say this distance as r. Now the gravitational potential of m2, with respect to this m1 is given by potential energy, and just simply writing it as potential energy, that is given by minus G gravitational constant into m1 into m2 by this distance r. So this is the gravitational potential of this m2 with respect to m1, or either you can say the gravitational potential of m1 with respect to m2, right? So this is the gravitational potential concept, and now we will derive the formula. Let's say I have a planet of mass m1 and of radius r, and I have a satellite, let's say, or any object of mass m2 here, okay, which is relatively very small compared to this m1. Mass of this object or radius of this object is relatively very small compared to this m1. Now at this point, I mean considering at the surface of this planet m1, or you can, if you consider this as earth, then I am considering the surface of the earth. Now at this point, the potential energy possessed by this m2 is, so potential energy at the surface I am writing as PS, no, let's say PES of m2 is given by minus G into m1, that is the mass of the planet, into m2, the mass of this object, by the distance between the center of these two masses, right? So that is from here to here. So I said right, the radius of this object is very small. Let's consider a tennis ball on the surface of the earth, or a small satellite on the surface of the earth. So the radius of the tennis ball or the radius or the size of the satellite is very small compared to this radius, right? So I am neglecting this one. So I am just considering the distance from here, this point or the center of this m1 to m1 just as r. So I have to write here r. So this is the gravitational potential energy possessed by m2 on the surface of this planet m1, right? And let's say to escape from the gravitational attraction of this m1, this m2 is subjected to a certain velocity, let's say u, okay? So this m2 is subjected to certain velocity u. So the kinetic energy on the surface of this m2 is, I have given some velocity u. Then this is half m u square. And the total energy on the surface is potential energy on the surface plus kinetic energy on the surface. And that is equal to minus G into m1 m2 by r plus half m u square, right? So this is the total energy of this m2 on the surface of this planet m1, okay? Now the another important point is, so I am writing it here, now this is very important. This body is subjected to u velocity and it escaped from the gravitational attraction of this m1. It is escaped now, okay? Now this body is very far from this object, okay? Now I have m2 here. Let's say relatively it's very far from this m1. So we consider it as infinite distance. So why I am saying this infinite is, let's say, the gravitational potential of this body, or gravitational field of m1 is, let's say, here, okay? So if you put any object here, it can attract, but if you put any object, it will not attract. The force is very small outside of this line, outside of this field. So we can consider this distance as infinity. You can take this point or this point or this point, it doesn't matter. If it is outside from this gravitational field, you can consider any distance outside of the field, consider as infinity. So now our object is at this point. Object is at this point, M2, and I said which is very far from the M1, and we consider as infinity. So what I am saying is, this M2 is subjected to u velocity here, but when it reaches this point, let's say when it just crossed the boundary of the field, or it just crossed the attraction of the M1, so that its velocity becomes 0. So I am saying that I am taking the minimum condition. If it got some velocity, then it's okay, but I am taking the minimum condition. Let's say it got the velocity 0 at that point, okay, at this point. So final velocity v is 0, right? Okay, now the gravitational potential at the infinity of this M2 is minus g into M1 M2 by distance is what? Infinite. So this is nothing but 0. Now the kinetic energy at the infinite is half m v. Let's say just v. So v square. That is nothing but v is 0. So half m 0 square is 0. So the total energy at infinity is 0. The sum of potential energy plus sum of the kinetic energy. This is 0. From the conservation of energy, the energy of this body M2 at this point and energy of this body, I mean the total energy of the body M2 here on the surface of the planet and at the infinite, both should be equal. So TE surface should be equal to TE infinite. Total energy on the surface should be equal to total energy at the infinite, right? So I am erasing this. Now I am balancing these two. This is the total energy on the surface, that is minus g into m1 m2 by r plus half m u square is equal to 0. Total energy at the infinity is 0. So this is nothing but half m u square is equal to g into m1 m2 by r. So this is m2, sorry. Yeah, this is m2. So velocity is given to this body. This is m2. Right here. M2 get cancelled. So simply your u is going to be, if you take 2 there, then 2 into g of m1 by r and square is 2. So this is the final formula for escape velocity. This is the final formula for escape velocity. Right? And if you keenly observe this, again the escape velocity is also independent of the object M2. Escape velocity, so I am writing this as VE. Right? So I said the U is the minimum velocity that is given to this M2 so that it can escape from the gravitational attraction of this M1. Right? So it already escaped from it. So you can call that velocity, that minimum velocity, as the escape velocity. When it escaped from the attraction of this M1, then that velocity is the escape velocity. So I am representing this as escape velocity VE, that is equal to root over 2 into g into m1 by r. And the very important point is, again this escape velocity is independent of the mass of the object, which is subjected to some velocity, right? This is dependent on mass of the planet, and this is inversely proportional to the distance between these two masses. Again, this escape velocity is again inversely proportional, right? The first point is this V is independent of M2. And the second point is V escape velocity is inverse proportional to the distance between m1 and m2. So this is end.